Okay, so let's dive in. We are looking at a moment that, people in the math and AI communities have been waiting for a very long time.
A genuine breakthrough. An AI system reaching, true elite level performance at the International Mathematical Olympiad, the IMO.
And our mission for this deep dive is to really understand the system, AlphaProof, because it didn't just compete. It earned a score that's equivalent to an IMO silver medalist.
And what's so fascinating is the how. It's this marriage of two really powerful ideas: the creative power of reinforcement learning and the absolute ironclad rigor of a formal proof assistant called Lean.
The final results are they're stunning. The system solved 4 of the 6 problems.
Which comes out to 28 out of 42 points. That puts it squarely in the silver medal threshold officially.
But the real story isn't just the score, it's which problems it managed to solve.
Exactly. That's where it gets really interesting. It focused on the non-geometry problems, so P1, P2, and
Okay.
P6.
So that was the monster problem of the competition, right?
Yeah. Oh, absolutely. It was the hardest one on the test. I think only 5, maybe 6 human contestants actually solved it.
And before this, AIs were, they were struggling with even the easiest IMO problems from past years.
Right. Solving P6 is a signal. It shows the system isn't just making tactical moves. It's demonstrating, actual high-level strategic reasoning.
So that success on P6 is the headline. But the real trick here, the thing that makes it all work, is the architecture. How do you even train something to have that kind of strategic thought?
Well, it all starts with scale, but a very specific kind of scale. AlphaProof is, at its core, an AlphaZero-inspired RL agent.
Okay.
But it's trained on a colossal data set, roughly 80 million formal Lean problems.
80 million. Wow. That's basically the size of all known formalized mathematics.
It is. And the fact that it's all in Lean is so critical because, RL is great at finding patterns and good enough solutions, but math demands 100% truth.
And Lean provides that guarantee.
It's the world's strictest editor. It doesn't care if an answer looks right. It verifies the DNA of every single logical step. The proof is either perfect or it's wrong. There's no in-between.
So that massive general training gets you most of the way there. But for a killer problem like P6, you need something more. And that's where this test time RL comes in, TTRL.
That's the special sauce for the hard problems. It's all about problem-specific adaptation. So when AlphaProof gets stuck, TTRL generates a whole new custom curriculum of problems.
Wait, so let me get this straight. The AI is basically inventing its own homework, tailored to its own weaknesses on that one problem.
That's a perfect way to put it. It's like having a personalized tutor who just drills you on the exact sub-skills you need for the one equation you can't crack.
That's incredible.
It then does a very focused RL training phase on just those variants, letting it develop really deep, problem-specific strategies.
Okay, but let's introduce a little bit of pressure here. The computational cost. I saw the solutions for these IMO problems took 2 to 3 days of TTRL compute per problem. That doesn't exactly sound like a breakthrough. It sounds more like a computational sledgehammer.
Yeah.
How scalable is that, really?
And you've hit on the critical caveat. It's not scalable, not yet. The effort far exceeds what a human could do. But the takeaway isn't about the current efficiency.
So what is the takeaway?
The takeaway is that the capability is now proven to be achievable. We know that this method, this targeted learning, grounded in verifiable data, can unlock reasoning that was totally out of reach before.
So to put it all together, you have this massive, broad learning grounded in the correctness of Lean.
And then you layer on this super focused adaptive TTRL for when the going gets tough.
And that's what gets you to an elite silver medalist level of complex mathematical reasoning.
Precisely. It proves that learning at a massive scale can produce these incredibly complex emergent reasoning strategies. And that leaves you with a really important question to mull over. Now that we know this is possible, the architecture works, the proof of concept is there. The question shifts from if to how fast. How quickly will the algorithms improve, turning these powerful multi-day systems into accessible, real-time collaborators for mathematicians working at the very frontiers of research?